In the previous session, we understood the various terms associated with simple harmonic motion. We saw some examples. We saw how velocity, acceleration, and displacement vary, how we can express them mathematically. So now that we have learned all these things, we can find out how we can determine the energy of a system that is in simple harmonic motion. We can take the example of a pendulum that is swinging back and forth. It has some energy associated with it because it has some mass and it is moving through space under the influence of some force. In the same way, a planet going around a star will have some energy associated with it. It will also be executing simple harmonic motion. So how do we calculate this? We can break down the energy of simple harmonic motion into two components, regardless of the specific example. So it can be a planet going around a star, or it can be simply a bob which is moving on a spring. In both of these cases, the energy of that system, the system as a whole, can be split into two parts. We can talk about the kinetic energy of this system, and we can talk about the potential energy of this system. Kinetic energy is associated with the velocity of the system, while the potential energy is associated with the position of the object which is undergoing simple harmonic motion. Now, you can have energy in a system due to its position when we are dealing with conservative forces. For example, the electrostatic force is a conservative force. The gravitational force is a conservative force. The force exerted by a spring is a conservative force, which means that if you are changing the position of the object under the influence of such a force, that is caused by a change in the potential energy of that object. That change can be positive or it can be negative. So in order to determine the kinetic energy and the potential energy of a system in SHM, let's look at how we can express the position and the velocity of the object at various instants of time. As we saw in the previous sections, for a system which is undergoing SHM, the velocity of the object is a function of time, it is a function of the angular frequency, and it is a function of the radius through which the object is moving. So we have the relation velocity being equal to omega a sine omega t plus phi, where omega is the angular frequency of the system, a is the radius of motion, and sine is the sine ratio. So the kinetic energy of a system Ke, which here we will simply call capital K, is given as half mv square. So we can square the previous term for velocity here. So we get the relationship K is equal to omega square a square sine square omega t plus phi multiplied by m multiplied by half. So this gives us half m omega square a square sine square omega t plus phi. So this is a measure of the kinetic energy possessed by this system. Now in this case, the term m omega square is the same as the spring constant of the system. So we can replace this term with another term called small k. So this simply becomes small k. So here we have an expression for the kinetic energy of a system undergoing SHM. On the other hand, we also have to find the potential energy of the system. For a system that is acting under a conservative force, for example, in this case, we are talking about a spring, the potential energy of the spring that is given by U is equal to half multiplied by K, which is the spring constant, multiplied by X squared. X is the horizontal displacement of the object which is undergoing simple harmonic motion. So the expression for X is given as X is equal to omega A cosine omega t plus phi, where all the symbols have their normal meanings. So X square is equal to omega square A square cosine square omega t plus phi. So this comes to U equal to half multiplied by K multiplied by A square cosine square omega t plus phi. you will notice some similarities and some differences. Both the kinetic energy K and the potential energy U have the small k term in common. They also have differences. So in one case we have sine square omega t plus phi, and the other case we have cosine square omega t plus phi. The total energy of the system is the sum of the kinetic and potential energies, that is K plus U. So this comes out to be half K A square cosine square omega t plus phi plus sine square omega t plus phi. As you can notice, the arguments in both the trigonometric functions are identical. So we can use the commonly used relationship sine square theta plus cosine square theta is equal to 1. So we get a simple relationship half multiplied by k multiplied by a square as the total kinetic energy plus potential energy, or the total energy of a system undergoing simple harmonic motion. Now, what is the significance of the sine and cosine ratios for kinetic energy and potential energy? Let's understand this with a simple example. Let's say we are dealing with a simple spring, and this spring is attached to a mass. So here we have a mass, and due to some kind of disturbance, this mass starts vibrating in the vertical direction. As the mass goes up, the velocity of the mass goes down. The mass is slowing down as it is going up. But as the mass goes up, the spring also compresses. So as the mass is slowing down, the kinetic energy of the mass is going down. So the system's kinetic energy is reducing, but because the spring is getting compressed, the potential energy of the system, the energy in the spring, is increasing. On the other hand, when the spring starts going back down, the kinetic energy of the system again begins to increase, while the potential energy of the system begins to decrease because the mass is moving down in space. This means that the two energies, the kinetic and the potential energies, are not exactly in phase. In fact, they are exactly 90 degrees out of phase. The point at which the kinetic energy of this system in SHM becomes minimum is also the moment where the potential energy of the system becomes maximum. Like a pendulum. In a pendulum, as the bob reaches the highest point of motion, its velocity is 0. So the kinetic energy is 0. But because the height of the pendulum is maximum above the ground, its potential energy is maximized. On the other hand, when the pendulum reaches the lowest point in its swing, the bob is moving at maximum speed, which means it has maximum kinetic energy. On the other hand, its height above the ground is minimum, so its potential energy becomes minimum. But regardless of the kinetic or the potential energies being where they are, the sum of these two energies at any given time will come out to be the same. The total energy of the SHM system remains conserved, unchanging over time.
Manorama Horizon. Learning made simple.